Hey everyone, welcome to today's conversation where we are going to be focusing upon black holes and things that you may have heard of to do with black holes, having to do with the information paradox, photon orbits, holography, and various ideas that are related really to the cutting edge of trying to get as firm a grip as we can on issues in general relativity and quantum physics and how they may come together in some of the cutting edge ideas that people are developing. And our guest today is Andy Strominger, who I've known for really decades. I first learned of Andy's seminal works when I was just a graduate student. He wrote one of the key papers in trying to make semi-realistic models of string theory using so-called compactifications, an idea that we've spoken about in some of these programs. Andy, together with Philip Candelas, Gary Horowitz, and Edward Witten, wrote this paper which introduced the idea of Calabi-Yau compactifications into string theory. And those are these beautiful shapes that you probably have seen, which may constitute the extra dimensions in string theory. And I did my graduate work exploring Calabi-Yau shapes and spent many years, many wonderful years, trying to elucidate some of their structure, as many others have as well. And of course, Andy, as I just mentioned, started that whole subject in its own right. He's done an enormous number of works, groundbreaking works in so many areas. So I'm thrilled to have him. So Andy Strominger is the Will E. York Professor of Physics at Harvard University, where he serves as the director of the Simons Collaboration on Celestial Holography, an idea that I think that we'll get to at least by the end of the conversation. And he is the associate director for theory at the Black Hole Initiative. Among his many awards is the 2017 Breakthrough Prize in Fundamental Physics. And Andy is joining us from his office at Harvard in Cambridge, Massachusetts. So welcome, Andy. Thank you for joining us today.
Pleasure to be here, Brian.
So I wanted to jump right in, if we could, onto some of the issues of black hole physics. And again, many people who watch these programs are familiar with some of these ideas. I thought it would be nice if we start with some of the history and then sort of walk through to the cutting edge ideas that you and many of your colleagues are developing. So where does the black hole story begin? Would you start with Carl Schwarzschild or further back? Where would you jump in with it?
Well, we could go further back, but I would start there. And it's an incredible, fascinating history in itself, and one that we're still at midway, the beginning of. We're not to the end of this story. And it starts more than 100 years ago when Einstein wrote down his field equations, which it is said he thought no one would ever find an exact solution of. And Schwarzschild proved him wrong only a few months later.
Yeah.
And he wrote down the Schwarzschild solution, which we now know describes the black hole. But the solution had so many strange qualities that it took 50 years to understand what it meant. And I recently was at a lecture by a historian of science who quoted an amazing number of completely wrong statements made by the great man Einstein himself,
Yeah.
including a paper in 1938,
Yeah.
decades later, saying that black holes don't exist.
Yeah.
And so just understanding what a classical black hole was took 50 years. And there was a great renaissance in the study of general relativity, which took place in Oxford and Princeton in the 50s and 60s, early 70s. People like Penrose, Bondi, John Wheeler, Stephen Hawking, Brandon Carter, great scientists. I could go on. And they finally understood what a classical black hole is. Of course, Oppenheimer and
Yeah.
Snyder. Yeah.
So before you get to that part of the story, which is vital, so just hold that train of thought. I want to go right there. But people may be surprised to hear that Einstein got so much wrong about solutions to Einstein's equations, right? He didn't write down the solution, Schwarzschild did, but where did Einstein go wrong?
Well, general relativity is a very subtle um, theory, and Einstein. I teach general relativity here, and Einstein would not pass all our graduate students understand general relativity. It's not that he wasn't a smart fellow; it was just that it takes a whole world,
Yeah,
decades to vet an idea that deep and to understand what it really means.
yeah.
And he really did not understand what the basic principle. Of course, he understood many things in his own way, but the basic principle of coordinate invariance, you cannot read those papers and think that he understood it.
So would you say that part of the subtlety is you have these equations, but trying to really interpret what combination of the symbols really reflects something in the external world and which combination of the symbols is just the vagaries of how you happen to express the mathematical system, and drawing the distinction is not easy.
Absolutely, absolutely. It's the physical interpretation of the equations that he got wrong. And let's also remember that the number of people working on general relativity, the first half of the 20th century was about quantum mechanics
Hmm.
and quantum field theory. And that's what everybody was working on. And so people didn't really, he never got a Nobel Prize for, there was never a Nobel Prize in the 20th century for any aspect of general relativity. And there were dozens so there were only a small number of people working on it until the 50s or 60s, and then all of a sudden people started working on it, and they came to some rather precise understanding of it, including the work that Penrose got the Nobel Prize for a few years ago, which showed that absolutely gave a rigorous mathematical proof that Einstein was wrong in his statements, that not only was Einstein wrong, but it was inevitable that black holes must form. Um, Pieces of that were there before Penrose, Oppenheimer, and Snyder, but they must form in the physical universe. That is a definite, unassailable prediction of the theory. This, by the way, was still practically 50 years before we saw them.
Yeah.
In sense, really saw a picture of them in the sky. That happened only 5 years ago.
Yeah.
That we had many kinds of indirect evidence, but there's nothing like seeing. Yeah,
Yeah.
and so we still continue. It's Einstein's theory of general relativity is the gift that never stops giving. If you're a physicist, there are still properties of that theory, deep properties, not adding commas and crossing your T's, deep structural properties of the theory that we're still struggling with today and learning more about.
Yeah.
Many things that we've learned.
And so
Um,
the image that you're referring to, and I think we even have it from the Event Horizon telescope. I think you said about 5 years ago. It's just about right. I think it was 2019 or so that they took the first image of the supermassive black hole in M87. Do we have that? If we can bring that up for a second, just so we can remind ourselves what black holes actually look like once you actually can image them with this consortium of radio telescopes. So, I mean, when you saw this image, I mean, did you have a particular response? Was it like, yeah, okay, of course, now we finally see them, or is it sort of more than that?
I cried when I saw that
Oh,
image
really? Wow.
because there's nothing like seeing a picture. And as you know, I've spent the last 30 many decades thinking about black holes, and there was this. I didn't realize it till I saw the picture, but there was this kind of nagging thing. What if these aren't even up there? And I remember on a panel that you were leading a conversation and we were discussing this, and this was 1 or 2 years before this picture. And the great Steve Weinberg said, well, I'm never interested in black holes. Didn't really think they exist. Maybe they exist, but we're never going to see them.
Hmm.
And, but they're here. And I think that this image, which reportedly was seen by 4 billion people, has ignited in the scientific world, both on observationalists and theorists like myself. What are these things? There's a picture of it. What's inside it? We don't understand how they work. So it's just a fantastic time to be a scientist. Yeah.
Now, mathematically, one can have a certain sympathy with Einstein's reluctance to believe in the existence of black holes, even notwithstanding all the more subtle issues that you're describing in terms of, coordinate systems versus invariants versus things that are artifacts of your mathematical representation versus real physical things. There is a real issue about black holes, about, the mathematics that Einstein wrote down. People often say it sows the seeds of its own destruction because at the center of a black hole, the mathematics doesn't make any sense, at least as Einstein would have formulated it. So what do you make of that, and how should we think about that?
Well, it's my take on that is slightly different than other physicists would describe it, but we expect every theory ultimately to break down. That doesn't mean the theory is wrong. With Newton's theory of gravity, Einstein didn't show that Newton was wrong. He just showed that there are small corrections to the equations which Newton wrote down, which are at that time were almost never measurable. And we need a better theory. And of course, that's our bread and butter as physicists, improving our laws of our knowledge of the laws of nature. And so I would say so if you start with some theory and you use its equations to see how things evolve, you might run into a regime where the theory itself breaks down. And that's good, because it's good for physicists, because if it breaks down, then we can look at how it breaks down and find the better thing that replaces it.
Yeah.
And so there really is nothing weird about general relativity breaking down. The weird thing is that Maxwell's theory doesn't break down. We know quantum electrodynamics breaks down. It predicts its own destruction under, for the experts, the so-called Landau ball.
Right.
And Einstein somehow didn't want general relativity to do this, and many people followed him in that. And that was one of the reasons he didn't like black holes, because they said that they did do this. Now, the oddity here is that it breaks down only inside a black hole, probably. That hasn't been rigorously proven, but probably only inside a black hole where we can't see the breakdown. And that's disappointing.
Right. But I have the following question.
Yeah.
And again, it's a weird kind of counterfactual, because now it's kind of beyond any real, skepticism that black holes are certainly out there. But if a student walked into your office and started with, equations in some theory, call it general relativity or whatever else, and you look at the solution that they present you with, and the solution itself has a singularity, wouldn't your inclination be to send the students back to do something else? Because it's the solution itself that they're presenting you that has a singularity, wouldn't that make you skeptical that the solution itself was reasonable or valid?
Well, the nature of these singularities is that you start with some sort of configuration in which there aren't any singularities. And then you use the equation to evolve it, to move it forward in time, and to see what happens. And no, I wouldn't be disturbed. I would just say, okay, these equations work up to some point, and then we get into some regime where we need better equations. Let's find them,
Right, right.
and
That's where we still are at that point, right?
that's where we are. Let's find
Yeah,
them.
right,
Yeah,
right.
yeah, yeah.
And so, given that these solutions, notwithstanding their singularity within their center, and perhaps worth noting, oftentimes people think of the singularity as a position in space. It's more a moment in time, so to speak. When you actually,
It's more a moment in time, right? If you have a star that collapses, it forms a black hole, and then later on, after it collapses, there's a singularity inside there. So stars above a certain mass limit, when they burn out and the pressure doesn't isn't enough to stop the gravitational pull, they'll eventually collapse, and then you'll get a singularity,
yeah,
which will be inside the black hole. So um, there's nothing disturbing about that. It's incredibly interesting, but not disturbing. In fact, it's wonderful that we have this interesting kind of situation going on that we can try to understand theoretically, and we could even now, take pictures of aspects of it and probe it in other ways.
yeah. And so, one of the thoughts in terms of going the next step is famously general relativity is a purely classical theory. It doesn't involve any of the ideas of quantum mechanics. And one might think that putting quantum mechanics in the story might help to resolve these singularities, take these ideas to the next step. And, Stephen Hawking was one of the earliest attempts, his work, to try to bring quantum physics into the story. And other people from different perspectives, Jacob Bekenstein, who was working with John Wheeler, in the 1970s, began to probe mathematically the edge, if you will, of a black hole, and found some very interesting things that have occupied people now for decades. So maybe take us a little bit through, Hawking's
Yeah,
ideas
so
there.
just when everybody was feeling kind of happy that they understood what a classical black hole was, um, Stephen Hawking had the idea. Well, okay, but the real world is quantum mechanical, and a black hole um, a black hole has an edge, and it's called the horizon. And light can't light can't um, get out of that edge. But in quantum mechanics, we have the uncertainty principle, and that is applies to everything, including the horizon. So you don't know, you can't know. Quantum mechanics forbids you from knowing exactly where the horizon is, and that allows things to sneak out. And so Hawking gave an astonishingly simple formula which makes almost no assumptions, that makes only very reasonable, simple assumptions. Um, a very ultimately a very simple argument combined with a very precise formula of exactly what comes out and what the probability of something coming out with a certain energy or frequency of all kinds of things, a universal formula. It's now inscribed on headstone in Westminster Abbey, I consider it, one of the most important formulas of the 20th century. And
And this is the black hole entropy formula?
this is the black hole entropy formula, or the formula for the
Temperature.
temperature. It's the
Yep.
temperature formula. They're closely related. It's the
Yep.
temperature formula. You have to
I mean,
combine his temperature formula with Boltzmann's entropy formula, which is also on his
that's on
headstone.
Tombstone too, right? A lot of
Tombstone.
epitaphs.
Yeah, you got to have a really great formula.
I'll ask you later what's going to be on yours, but
I don't have a worthy one, but
and
so
anyway, we can actually show the audience. Obviously, you don't need to show you, but why don't you bring up the entropy formula for a black hole, just so people can sort of see the structure of what that formula that combines Hawking's temperature together with Boltzmann's formula.
oh
That
yeah,
yeah,
yeah, yeah. So this formula is a formula for you. We can think of it. Read on the left, uh, the number of gigabytes. How many gigabytes you could fit into a black hole? How much information it can store? And it's proportional to the area of the black hole times Boltzmann's constant times the speed of light cubed divided by 4 times Newton's gravitational constant times h bar, which is Planck's quantum constant. So this is a first a very unusual formula. In a way, no formula has ever appeared like this in the history of physics, because it essentially relates every large area of modern physics. It's got a relativity, it's got gravity, it's got statistical mechanics, it's got geometry, and it's a relationship between all these things, and it's universal. It applies to any black hole of any shape or size moving around with charge, with angular momentum, and it's simple. And the best thing about it is, this formula was not, if I take my smartphone here and I want to know how many gigabytes it stores, there's 2 ways I could do it. I could start loading photos on here, 1 gigabyte a piece, and at some point it would tell you memory full. But that way wouldn't wouldn't tell me how the information was being stored. The other thing I could do would be well, there's no screws on here. I could try to take it apart, find the chips, and count them. And if I could count all the chips there, I would know and I would understand how the chips work. That's what it would mean to really understand that I've got however many it is, 16 gigabytes on my phone here. What Hawking did was the analog of he inferred this formula.
Hmm.
It was the analog of just putting, it was a Gedanken experiment, but it was the analog of just seeing how long it takes to fill the iPhone up, and therefore the information storage constant must be whatever it is, this area law. And we need to take the thing apart. How is this information being held inside the black hole? And doing so is, a central goal in modern physics.
And one of the key things about the formula, beyond your noting the amazing fact that it blends so many different areas of fundamental physics through those constants on the right-hand side,
Yeah.
On the far right-hand side, but the fact that the information, the gigabytes, the storage capacity that you made reference to scales like the area of the black hole, whereas like you'd think most people intuitively think that the amount you can store in something scales like the volume.
Right. So the first thing you know is if you want to if you want to double the number of gigabytes, you have to have twice as much volume in here. It's not the surface area of the phone. Well, of course, the phone's very flat, so
Yeah, it's a little misleading.
the phone's very flat, but it's not the surface area of the phone. It's the
Yeah,
volume. If you're trying to stuff more chips in, you need more volume, not more area.
yeah,
And that is going to bring us, and it is very weird. It's as if the black hole only allows you to put chips on its surface,
yeah.
as if there isn't an inside to the black hole. And that is going to later get us into the holographic principle, but I think
Well, I'd
I
love to
we're going
almost
better.
get there now, but we have a little visual which illustrates what you just described in terms of information storage on the surface area of the black hole. If we could maybe just take a quick look at it, and it kind of follows a Gedanken, like a thought experiment, like much as you made reference to, Andy, where if you have a black hole and you sort of throw one additional piece of information in, like that little yellow dot, like one piece of information, the area should grow, by 1 Planck unit. And then just to illustrate the point that you were making, if we sort of cover the left black hole, with a grid where each of those little squares is, storing, 1 unit of information, so to speak. If we explode that surface and paint it on the slightly larger black hole, which we believe expanded its area to accommodate one more unit of information, when we try to put all those little squares on it, they should get really close to filling the surface area, but miss by one because it grew, by 1 square unit in the units that we're talking about to illustrate that point. So in essence, that's sort of what Hawking was showing.
Yeah.
And so the natural question is the one that you're asking, you know, how far? So Hawking inferred this. It was sort of a brilliant tour de force to put together, ideas of quantum mechanics and general relativity and statistical mechanics, into this one beautiful, and information theory, in essence, into one beautiful formula. But for decades, people struggle to identify exactly, or at least in some more rudimentary way, where the degrees of freedom were being stored and how they were stored. And that really takes us to work that you and Qumran Vafa did, which was really the huge breakthrough using string theory to give insight into the basis of this formula. So, if you can just give a sense of what you and Qumran Vafa did.
Well, so if you want to, you see, this formula has an H bar in it and it has a Newton's constant in it. So clearly, if you're going to really understand it, count the chips, you're going to have a theory which is fully consistent with both quantum mechanics and general relativity. And string theory, I would not argue that we know string theory is a theory of nature, but I would argue that there's overwhelming evidence that it's a consistent mathematical theory which contains general relativity and quantum mechanics. And now we've understood this more or less since that it was a consistent theory since the early 70s, and before either of us were physicists. And but sometime in the 90s, so if it's a fully consistent quantum theory of gravity, it better, and you can understand everything, it better reproduce this formula. You better be able to see where the chips are and count them and see that Hawking got it right. And the problem was, it's a mathematically very difficult problem, but over the decades, starting in the early 70s, we just gained more and more in leaps and bounds mathematical control over the theory. And sometime in the mid 90s, it became clear that we understood enough that, or that we were going to be able to calculate this. And I realized this in the early 90s and was just like, okay, we got to do this, because if it doesn't agree with what Hawking said it has to be, then something is really wrong. String theory would be wrong, or I don't know what. And and if it does, it you know then we can understand something about Hawking's mysterious formula. And of course, it did. And we did look at black holes which occur, certain kinds of black holes which appear in string theory, and we were able to really tease them apart. And if depending on where we go, I can talk about more about what we found there. But
Yeah, I wish you would, because I think it sets us up well for the developments in holography and Juan Maldasena's work and conformal
right,
field theory and things like that.
right. Okay, so we found, first of all, string theory contains other kinds of objects other than strings. So strings are one-dimensional extended objects. And around this period, we learned that the theory also contains, as solutions, just like a black hole is a solution of Einstein equation, things that are membranes and various kinds of extended objects of higher and higher dimension. These all played an important role. And now it's entirely possible, as most people are familiar with in everyday life, that uh, a single phenomena, a single object, can be described differently. Like, to take a ridiculously simple example, my cup of tea here, we could say, well, you can't see, but we could say it's 10% full, or we could say it's 90% empty. Those are the same statement. And before I got to the end of that statement, you could realize they were the same statement. But there can be examples, and indeed are examples, in which it takes hundreds of people working for a decade to understand that there's two different equivalent descriptions of the same object. That's known as a duality. And so Kumran Vafa and I showed that for these certain stringy black holes, they could be understood as a kind of bound collection of these extended objects, but more importantly, they were formed in such a way that it was a two-dimensional, one space, one time dimensional object known as a conformal field theory. So a conformal field theory is a system which lives in one space and one time dimensions. It's fully quantum mechanical. It's fully consistent with special relativity. And these are ubiquitous objects in modern physics. They're seen in laboratories where, for some reason, you can have the uh, dynamics systems which are confined to one spatial dimension, like a wire. If you have electrons moving up and down a wire, that's described by a conformal field theory. So they occur in many kinds of systems, and they have an incredibly rich mathematical structure. If you look at my bookshelf back there, I would say there are at least 10 textbooks that are each this thick on the properties of conformal field theory. They're the thing that we understand the most about. And so it's really exciting for us to take a black hole and show that it had an equivalent description as the very kind of mathematical object that we know the most amount. And this was the first example of what's now known as ADS CFT duality, where you describe, you have two descriptions of the same thing, which just look wildly different, but it took decades to sort this out. And in the case of the black hole, we had the simplest of the examples. And this not only reproduced Hawking's formula for the entropy of the black hole, but it reproduced answers to other questions, like if you throw something at a black hole, how does it bounce off? How does the black hole evaporate? All kinds of things were answered. So it was a very, very rich example of two inequivalent description of the same object, which started from different points of view.
Yeah. And so in your calculation with Kurman-Baffa, when you got Hawking's formula to reproduce it through a very sophisticated but wonderfully straightforward counting argument, you built the black hole in essence out of the ingredients that you made reference to, strings and d-branes, and in essence you just showed how to count up the degrees of freedom, and it equaled the value that Hawking wrote down.
We just bulldozed through it. But having bulldozed through it, as the years went by afterwards, there were all kinds of important, that often happens in physics. The first time you do something, you don't quite know which way to go. It's like Lewis and Clark, trying to get to the West Coast. They go around the mountains, and they went down, and then they went back up. And when they got there, they met I think it was the Shoshone Indians, and they told them, you know what, the place you were 3 weeks ago is only 2 days walk through the pass there. And so that's what Kurman and I did. We took the long route, but now we have learned where the passes are.
Yeah.
And there are a lot of interesting, conceptual developments that came out of that.
And one of the ones that's worth spending a moment on is one that people still argue about, which is the so-called black hole information paradox, or puzzle, or mystery. Again, that relates very tightly to Stephen Hawking's work. And what is that puzzle like, and where do you stand on it now?
Yeah, let me back up and say a few words about the information puzzle. So Hawking, there were really two puzzles, and they were in two different papers, really, that came out of Hawking's work. The first was just understanding how a black hole could store so much information. That's counting the gigabytes. Then the harder question is how the information gets out. That is trying to understand how my iPhone is connected to the internet. How do I get a text message? And Hawking argued that a black hole will evaporate, and there is a description of that evaporation process in which the stuff that comes out is boiling off the surface and doesn't know anything about what's inside the black hole. And therefore, all the information that goes in the black hole, after the black hole evaporates and disappears, all that information is lost. Now, okay, doesn't sound so bad at first, but when you think about it a little while, it is a complete unmitigated disaster, because what it really means is that there are not laws of physics, not exact ones, because there's a random nature of what happens. So physicists, by and large, I think one would have to say, are a rather arrogant bunch. And we at least work on the premise that if we knew everything about the present and all the laws of physics, we could predict the future and retrodict the past. And there isn't some random stuff that just happens that isn't governed by the laws. We like to think that we don't think we've gotten there, but we like to think that in principle, physics can explain everything. Now, maybe that's wrong, but that's the premise we all are working under. And we really don't know what to do if somebody says, well, once in a while, we're just going to it just gets messed up and something else happens and there's no explanation for it.
And one way of thinking about that randomness, presumably, is I could have two black holes formed from completely different historical processes that ultimately give rise to exactly the same statistical radiation, because that radiation doesn't remember anything, doesn't know anything about how the black hole forms. It's just boiling off from the surface.
Yeah, yeah. So a peculiar things about black holes is that according to Einstein's theory, before you take into account quantum mechanics, every black hole is not every black hole of the same mass and spin is not just similar, they are literally identical. John Wheeler phrased this by saying black holes have no hair. There's no um, uh, identifying features of a black hole. And that is very different from a star. Stars are composed of a lot of molecules. If you find two stars with the same mass and spin, they'll have different chemical composition, they'll be different in innumerable ways. Not so with black holes. So when a star collapses into a black hole, they're basically all the same. So, and then after it collapses into a black hole, it starts to Hawking evaporate. According to Hawking, the evaporation only depends on what on the mass and the spin and maybe charge of the black hole. So that's what's called the information problem. We have some insights in string theory, but I hasten to add that we don't. There's still a big jump from string theory black holes to M87 star and other. They're kind of different stripe of black holes. Maybe we'll get to that later. So they're even with the information storage, we have a lot to understand. But the information puzzle, the history of that is just kind of fantastic. At least once a year, somebody claims to solve it. Nobody believes them. There's some arguments. People have really strong feelings. It's all over the map. And I think the space of possibilities I don't mean to say that we haven't learned a lot about how the information problem might eventually be solved. There is consensus on some proposals definitely being wrong, but there is no consensus now, and there's no clear solution of the information paradox. There are people out there who believe that they have some understanding which is close to a final answer, but we don't know yet. We don't know where the story ends. And
But you have but presumably, do you have any doubt that the information is preserved? Is that a question in your mind at all?
well, okay. So two things happen. Hawking, of course, famously um, argued that information was destroyed, and that is just a fact of the real world. But you can't just say that information is destroyed. You have to say, well, what do we do now? We just close down physics departments, or and there aren't laws of physics, or we need some other way of writing down laws. We can't use Schrodinger's equation anymore. He's saying that Schrodinger's equation wasn't good, and there was never an alternative, even in the 50 years. He proposed an alternative to quantum mechanics in which information can be destroyed, a so-called dollar matrix. That was quickly proven to be inconsistent. He dropped it. Nobody discusses it anymore. And I would say there was actually a vote taken at a conference. When was that? Early 90s in Santa Barbara. Do you think information is destroyed or not? And it was not far from 50-50. I think the tide turned when around the string theory developments, not just what Vafa and I did, but what the ADS-CFT, that Maldaceno's contributions and so on, the tide turned. If you've shown that the black holes, why should the black holes bother to be able to store precisely the amount of information that is required, but not ever let it out in or out? That by Occam's razor, if that works, you would think that the information would come back out. So I wouldn't quite say physicists have to bet. You have to bet on, you have to guess. And, I would say there's maybe 1,000 people in the world who have thought about this long enough and hard enough to have an opinion on it. And it was 50-50 in 1990, and now there's two people who at least confess to thinking that information is destroyed, and the other 998, which would include me, I don't want to spend my time thinking about how you might reformulate physics if information is destroyed, because I think it probably doesn't go that way.
Right.
But that's very different from knowing. People are, I wouldn't say, yeah, I've made my bet. I'm betting my lifetime's work on the guess that the information does come back out, because there's been a lot of indicators. You would have predicted, if you thought that there's been a lot of sharp calculations and but no proof.
And for me, one of the most convincing arguments, and I wonder if it ranks as high for you, if you use, just speaking slightly technical for a moment, this ADS-CFT duality that you made reference to before, where you can do variations on that theme, of course, that where you can have a black hole, in the volume part, in the bulk, as people often describe it. And when you look at the dual description, your 10% full and 90% empty duality, scaled up to this more sophisticated realm, the dual description of that is just some ordinary quantum field theory at finite temperature, which we know well doesn't have any information loss problems. And if these two things are the same, obviously there aren't black holes in the real world, but then it's such a tight argument showing that the information must be preserved.
There's two things there. There's whether you think that it's preserved in ADS black holes, anti-de Sitter black holes, and string theory. That seems very hard to disagree with. But then a lot happens when you try to go from, there's some qualitative differences between that problem and the M87 problem, and but I think that that intuition is very likely basically correct, and that's why I bet on, yeah.
So we'll get to some of the attempts that you and your colleagues have made to take this holographic idea, physics that takes place on a boundary, somehow being the dual description of physics that takes place in the volume. Evidence already comes from what you explained already. If information in a black hole somehow stored on its surface, then we have a surface theory somehow describing things in the interior in some sense. And you and your colleagues have tried to push that idea from the domain in which it has been formulated, say by Juan Maldacena in anti-de Sitter space, trying to push that to flat space. So we'll come to that a bit later. But I want to return to these more real black holes like M87 or Sagittarius H star, the black hole in the center of our galaxy.
Yeah.
Because, in fact, why don't we bring up, the one of the photos of the Event Horizon Telescope? Because you've spent some time with the Event Horizon Telescope team. In fact, you're collaborating now to sort of deeply understand the image and to even do better to try to understand things such as the so-called photon orbits
Yeah,
that happen in these environments. So
yeah.
maybe you can take us through, some of the inspiration from the image, and we have some nice animation that you provided us that we can get to in photon orbits as you describe it.
So this is the photo that my colleagues here uh, took, um, and what we're seeing here is hot swirling gases that are going around a black hole, and the black hole is in the middle of that photo, and of course it's an incredible. Those guys, they're amazing. They were driving to mountain peaks in Mexico, sometimes being held up by robbers, waiting for good weather. They had so much data they had to transfer. They were running around in suitcases, and I mean, these guys are great experimentalists, and they took a great photo that didn't didn't seem like it was going to be possible, but they did it, and they did it on a shoestring for an astronomy. Um, but in the end, from this photo, um, we the question that they asked me, when the photo was taken, how can we learn about the actual black hole in the middle? Like, if we look harder and harder at this photo, how are we going to learn? The prize here is the black hole that's in the middle, and we don't want to. We do, of course, astronomers or scientists are interested in everything. We'd like to know what those gases are and what the temperature is and how the jets formed, and all those questions are fabulous deep science. But I think the real prize is the black hole in the middle. And how are we going to learn about that? How are we going to see the curvature of space time? And one sharp question is, how are we going to see what the spin of that thing is?
Mhm.
And that turned out to be a question which, uh, a team of theorists here, working with the observers, came up with an answer, and maybe we'll get back to this later. But it it in my mind, it's also gave us new ways to think about these quantum questions. Just the interaction between observers and theorists, and so that's when we analyzed the structure of. We did find this question: how do we learn about um, the curvature of space around the black hole? Has a very beautiful answer, and even more surprisingly, it can actually probably be measured, and the experiment required to do it looks just barely doable. So we're pushing the edge of, you know, modern technology.
And so what is the experiment, and what will it seek to measure?
Okay, so there's something called the photon ring, and maybe do you have a
I think we do have an animation that we can bring up.
yeah. So it turns out that space is so. This looks like it could be an animation of planets orbiting the sun, but these are actually beams of light which are orbiting a black hole. And the yellow region there is the region of space time which contains these orbiting photons. That's known as the photon shell. And I just want to mention space has to be really curved for this to happen. You know, what Eddington saw, he saw light not going in a straight line, 100 years ago, but he saw light rays whose orbits were deflected by one part in, I think, 100 million. These things are going around in circles. Um, the universe is very different in this region of space time.
Yeah.
And now here we're seeing all the different orbits, and these orbits are results of calculations using Einstein's theory of general relativity. And the structure of these orbits knows follows from Einstein's equation, but turning it the other way around, if you see the orbits, you can build back up. It contains all the information about the curvature of the space-time. So if you can see these orbits, it's very different than just looking at more details of the swirling gas around the black hole. These are the things that we want to see, photons that have rays of lights that have been on these orbits.
Now, to see it, obviously, those photons at some point have to be released, or else,
Right,
you'd never.
right, right. And maybe that's in your next.
Yeah, I think. Do we have a? Yeah.
Yeah, okay. So we have a black hole there, and we can see there's a black hole. That's light rays like what Eddington saw, just slightly deflected, but they can be deflected a lot. And in fact, they can orbit some number of times. Here we've got it, orbiting around, and they appear in a little ring that is inside the direct image that the Event Horizon Telescope. So this bright ring here has not been seen, but it was close to being seen. If you had 5 orders of magnitude better resolution, not 5, a factor of 5 better resolution, you would see this ring. And so we want to see that ring. So to really see that black hole, you want to see that ring. Those are the photons that almost orbited some number of times. And in fact, there's a whole nested sequence of rings of photons that orbited different numbers of times. And there's a huge, everything you want to know, and this was what we worked out, everything you want to know about the geometry around the black hole is encoded in the ratios of the sizes of those rings.
And that's a purely general relativistic classical analysis, or?
That's a purely general relativistic classical analysis. So let me give an analogy. If you are in a department store trying some clothes on, and you go to a mirror, you look in the mirror, you can see whether you like your clothes. Okay, you learn how you look. But now imagine you're in one of these things. So a black hole itself is a mirror, because light from your head can head to the black hole and go around and come back. But it can go any number of times and come back. So it's like one of those three-sided department store mirrors where you see an infinite number of images. And now if you look at the relationships of the different images, it doesn't matter whether it's you looking at the mirror, me looking at the mirror, any of our audience looking at the mirror, you'll come up with the same conclusion. You know, the clothes might look better on you than on me, but we'll agree on, we'll come up with the same conclusion about the structure of the mirror and how light moves around in them. And so that is what we need to do to to um, to learn to really see the geometry of the black hole.
And this is the sharpest, simplest way of getting at that information.
This is the only way that we know of,
Yeah.
of getting at that information. Now we need to get better resolution, and to get good resolution, you need a big telescope. And just to see that, the donut picture you showed in a few minutes ago, you needed a telescope the size of the Earth. If the Earth had been half as big, you couldn't have done this. And even more interestingly, it turns out that M87 star is twice as big as they thought before this picture. If it had been the size that was expected, we still wouldn't have a really good picture of a black hole.
Yeah.
So this was just on the edge of what was achievable, and in order to see it, you had to use the whole Earth as a telescope. Now, there's no radio dish over our heads right now. We didn't turn the whole Earth into a telescope, but we did something just as good, or they did something just as good, which is they synchronized many of the radio telescopes on Earth, and networked them, coordinated them using atomic clocks. Fantastic experiment. Coordinated them using atomic clocks, and that was just enough to see this. How are we going to get the other factor? How are we going to see that photon ring? So, you know, theorists love to come up with amazing things you could measure, but usually they're not measurable. So to me, when I first saw this, this is so cool the way these photons orbit. This is never going to be measured. But my observer friends in a team led by Michael Johnson said, hey, let's put a telescope in space. And okay, but then how far do you have to go out in space? Maybe you have to go out, to the next star, or what do you have to do? Well, it turns out that 22,000 kilometers is enough to see the first ring. And if you go to the moon, you can see the second ring. If you go to where the James Webb Telescope is, you see the third ring. So not only is there a beautiful way to see this, but it's just at the edge of what might be doable with current day technology.
And one additional receiver at those distances is potentially adequate to get the data that you need to see the rings?
Okay, so we wrote this paper about how to do this 5 years ago. I was waiting for somebody to come along and say, "Oh, you're not going to be able to see this." Another obstacle here is, for the Event Horizon Telescope, they didn't send the data around on the internet.
Yeah.
They had trucks with hard drives in them that they drove. and brought them here and then analyzed the data. How are you going to get this information down from space? Well, you got to beam it down with a laser, something like 64 gigabytes per second, you know, a lot. Um, so I was waiting for somebody to say, okay, that's really cool, but you're never going to measure this. But it's been 5 years now, and it actually looks like it's going to happen. So I think this is going to be one of the most exciting experiments, uh, in a long time.
Is
Uh,
this the first time that you've had something that made a direct observational prediction that someone is actually going out to try to measure?
um, well, they're also trying to measure my predictions of the gravitational spin memory,
Yeah.
which came out of the celestial holography. But I've wanted to, I've wanted to make predictions. I made some other predictions for the Event Horizon Telescope about the polarization structure, but they were, that's what usually happens. They were 5 orders of magnitude away from being
Right.
measured. Okay, so I've made probably dozens of predictions, a dozen maybe predictions that were, and of course predictions from string theory, which are 30 orders of magnitude away from being measurable.
Right.
But I've made some. I've done better than that. I've done 5 orders of magnitude, but 5 orders of magnitude is too much.
Right.
1 order of magnitude, you can hope to get it. And so it's very exciting for me.
Yeah. Huge.
It's very, very exciting for me.
And so, what's the status of actually building the device and launch? Is there a timeline for?
Well, we have the 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 Black Hole Explorer uh, um, collaboration. We have a proposal. We're shopping around. If any of the audience wants to write a very, very big check, we'll we'll take it. Uh, Seriously,
Yeah.
but um, uh, NASA is very interested. We're submitting a proposal.
I mean, what is the price tag? I don't have a good sense. Is it how many figures is it? Is it like 9 figures or?
Well, okay. So it's learn a lot of interesting facts. Sending a dedicated satellite mission, it's $1 million a pound, and or $1 million a kilogram maybe, and and our experiment will be hundreds of kilograms. So we'll it'll be hundreds of millions of dollars just to see the first ring. But of course, that's a lot of money. But also, it's interesting because it's on the cutting edge of technology, doing all these things, and so there's a lot of interest in doing things in space. Um, when you want to do something in space, which I never have before, it seems the price tag goes up by a factor of 100,
Yeah.
and the interest also goes up by a factor of 100.
Right.
So, it's a lot of fun.
I mean, I've heard something people throw around the number, in 2031 was a target for launch. Is that still a number that your collaboration is anticipating?
Yeah. 2031. If our proposal, if there's no snags, and NASA, we have to do a study, right?
Yeah.
Of how much it's really going to cost, and again, is there something, refrigerator won't go low enough, and there'll be too much noise or whatever, um, and I haven't, in previous scientific explorations, I haven't interacted with this kind of uh, well, I did build an experiment as an undergraduate, but I haven't interacted with this kind of, and these people are amazing. They're dedicated, they're brilliant.
Yeah.
They it's just inspiring to see.
But maybe that guy who's in charge of the incoming Department of Government Deficiency could,
That's right. That's right. That's right. And, well, we probably, yeah, we have to launch a satellite.
yeah,
Yeah.
right, right. Um, you mentioned earlier how conformal field theory, this idea of transformations that change the scale but preserve angles, is one way of sort of thinking about this trend. It's sort of a ubiquitous idea. I mean, certainly anyone who's looked at the basics of string theory knows that you immediately encounter conformal field theory in the first semester of a course on string theory. It's there, and in so many other places, both in the real world and in theoretical undertakings. I have not had time to study it, but I have heard, and so maybe you can just give a few words on it, that you've also been studying conformal transformations of these photon orbits and relating that to transformations of the ring down of a disturbed black hole. Maybe just say a few words about that.
So the classic interaction between theorists and observers um, is, a theorist makes a prediction and observer goes out and experimentalist goes out and measure it, or experimental finds something weird and the theorist explains it. But more important than that, or as important as that, is much more indirect kinds of interactions where you're talking to one another, trying to explain things to one another, and it inspires you in your own questions that you're after. And that's definitely happened here because one of the huge problems, so we we had this success, which we've talked about in string theory with understanding how the information is stored. But we think that this number of gigabytes, that this formula gives the right number of gigabytes for M87 star. And we don't know if our world is described by string theory. And even if it is described by string theory, it doesn't seem right that we should have to use string theory to explain it. We should be able to understand it from some sort of more basic. Hawking made his derivation just assuming quantum mechanics and general relativity. We should be able to derive a method to count the gigabytes just using quantum mechanics and general relativity and their properties. And one of the outstanding problems is, how do we understand the formula, the Hawking's entropy formula for M87 star? And we can't use string theory because we don't know if string theory is describing our world. And even within string theory, there's some black holes that we don't know how to do the computation for, and that would include the Schwarzschild black holes, which are themselves. So we can't really use string theory for this, but we can use intuition from string theory. In other words, the trick of going, especially now that we know how to go through the passes instead of following the river all the way along, we should be able to use intuition from string theory. And it might be that, M87 star also has a hologram. It's surrounded by a hologram. And these holograms are usually, the emergence of the hologram is usually related to a conformal symmetry. Now, it turns out that I talked to you about these different orbits and these different photon rings corresponding to different orbits. We recently showed that they are related by a conformal symmetry. And there is a conformal symmetry which we mathematically proved acts not it's a little its structure is a little different than the stringy black holes, acts not at the horizon but at the photon ring. And so could this conformal symmetry be related to the understanding the quantum structure of any real black, any astrophysical
Yeah.
black hole? And moreover, so I don't think we mentioned where the word holographic comes from. It comes from hologram. Um, you have a hologram and you shine a laser through it, and that produces the image. And a black hole, according to Hawking's formula, seems like a hologram where the information about the image is stored on the surface of the black hole. And the black hole interior and the space time itself emerges as the holographic image. So we thought, whoa, this photon ring, we'd never thought about it much before. But if you look at some of these simulations of, either the LIGO simulations of merging black holes, this photon ring is like the important surface, the interesting surface that's outside the black hole. So a natural question is, does the holographic plate, is the photon ring the holographic plate?
Hmm.
And that is a mathematical question that, the theorists can run with. We don't have the answer to that question. I don't want to be advertising this as something that we understand. I'm advertising it more as a fun question and as example. You ask and you explore 100 questions like this, and one of them works,
Right.
right? So I'm not advertising this as the new way to think about, but it's an example of a wonderful example of how talking to people outside your intellectual sphere jogs your mind and brings you to think about, interaction. Cross-disciplinary interactions can really be just incredibly stimulating.
And just to give people a sense, just have an image in mind. I gather for a Schwarzschild black hole, the photon ring would be at about one and a half Schwarzschild radii, right? So you'd have the event horizon, and then 1.5 times that radius is where this other surface would be located. This photon ring.
Would be 1.5 times, yeah, the radius.
Yeah, and for a rotating black hole, it's too complicated a formula for me to have in mind. It's got too many cosines in it. But there's some other
Yeah,
well-known mathematical formula for
yeah,
where this other surface would be outside of
yeah, yeah, yeah,
a
yeah.
black hole.
Well, when it rotates at the maximal rotation, it goes right to the.
Yeah, right.
It touches the.
Yep.
the
And so that's exciting, that there are these observations which may actually connect with these mathematical ideas you've been developing. But one of the other things that also potentially has a observational experimental import that you made reference to is this idea of trying to push this idea of holography, which again, famously, many people were responsible for it. You had Critical Insights, Lenny Susskind, Gerardo Tuft. Often people look at Juan Maldacena as the sort of culminating, putting it all together in the most precise mathematical way at the time, 1997. That there's this relationship between anti-de Sitter space, in the bulk and conformal field theory on the boundary. But, famously, we don't live in anti-de Sitter space. So the observations suggest maybe we live in de Sitter space, negative versus positive vacuum energy. But it could be that the dark energy decays over time. Maybe in the far future it's just flat space or asymptotically flat space.
Or we could just think about, I mean, right. So just to restate, so we came to an astonishingly detailed and compelling um, understanding, not just of how black holes were consistent with the holographic principle, but how a whole universe could have a holographic description where you have a conformal field theory in some different number of dimensions, actually, that doesn't have gravity, that serves as the holographic plate, and the whole space time emerges. It's a spectacularly precise and beautiful construction, um, of which Moldacina was the many people contributed, of course, but um, was the prime originator, and but it only it does describe a whole universe which is holographically emergent.
Yeah.
And it's such a precise and beautiful picture. One would like it, this holographic principle. It would be weird if it applied to, I'm big on Occam's razor. It applies to black holes, and it applies to whole anti de Sitter universes. Shouldn't the holographic principle somehow be a basic principle of what happens, that space time is emergent in any situation, including uh, our own universe? How can we understand it for our own universe, which is, to a very good approximation, flat? So we could be just discussing our own universe. We didn't know it wasn't flat until whatever, 20 years ago.
Yeah.
And in other words, we didn't know that there wasn't. We knew it wasn't flat, but we didn't know that there was dark energy until 20 years ago. And so so it's an important and very difficult problem to understand what is the general statement of the holographic principle. How does it apply in space universes like our own, or any universe that isn't anti-de Sitter space? And this, to me, seems like not only is it a pressing and important problem, but one that we are beginning to develop tools that we have a sharp way of thinking about. And not just, so universes like our own, which are consistent quantum theories of gravity, and without assuming that the world is made of strings, which it might be. I'll be very happy if it is, but it doesn't seem like this holographic principle. One would like to think that the holographic principle is sort of even deeper and more fundamental than string theory, and that that we can understand it without using string theory, from some first principles, just as Hawking, who I regard that as the beginning of the holographic principle, just as he derived that before string theory was even really understood. Yeah.
And so if this holographic idea is as general as you imagine, and it would be a beautiful thing if it is, I'm asked all the time when I give some lecture, general context that mentions the word holography. They always, the question is, where is this holographic surface? If it works here in our universe, tell me where that surface is.
Yeah. Right. Well, okay. So, we don't know. but but there's been a promising guess recently, and the sort of step zero, which which was step zero in ADS-CFT, is identifying the symmetries. So the symmetries, if you have both sides have to have the duality. So there's two dualities. There's the image and there's the plate. They both have to have the same set of symmetries. Otherwise, there's no hope that they describe the same fundamental object. And that that was not only step zero. If you look at Moldacina's paper, that is gets most of the mileage. You get almost to the end of the paper just by this is symmetries. This is the only way it could work. Now, in the subsequent 25 years, there was just an insane number of precise calculations that show that that's the way it is work. But in the beginning, it was like, what else can happen?
Yeah.
Um, and Now, it turns out just in the last 10 years, it's been shown that, that quantum gravity in flat space, and this demonstration does not invoke string theory in any way. It invokes some theorems that are there are a precious few theorems that you can prove about that must apply to any theory which consistently incorporates quantum mechanics and general relativity in flat space. And the very first of those, it's called a soft graviton theorem. The very first of those was famously proven by Steve Weinberg.
Weinberg again, right? Yeah.
Yeah, he's a great.
Yeah.
It
Amazing.
was a privilege to share the stage with you and him.
Yeah.
And he proved this theorem in 1965. He says, "I don't know what solves the problem of quantum gravity, so I'd like to follow Weinberg. I'd like to start every paper with, I don't know what solves the quantum problem of quantum gravity, but whatever it does, it must obey this soft graviton theorem." And he proved that theorem, and there's a lot of interesting stuff to say about that theorem. But
In fact,
Freddie,
can you jump in for a split second, almost as a footnote? Soft gravitons. Just maybe describe in terms of low energy and what that's all about.
okay, so a graviton is to gravity what a photon is to light, to electromagnetism. It's the quantum particle of gravity. And soft is a word that physicists use for something with a very low amount of energy. Now, the way that physicists often like to characterize a theory is by what's called, is they like to scatter particles. So you start out, so this is what you do at accelerators. You start out with electrons or protons and you throw them at each other. Something very complicated happens, and then you measure what comes out. And those are called scattering amplitudes. And this is what is done at accelerators, scatter particles. Now, it turns out that if you know everything about scattering amplitudes, you're kind of done. You've understood everything. That incorporates all the information about there are other kinds of questions you can ask, but they can all be transformed into a question about scattering amplitudes. So we'd really like to understand these scattering amplitudes. And now you can ask the question, suppose one of the scattered particles is you have an incoming, I'm having a little trouble with the camera here. It's backwards. Okay, so uh,
Chiral symmetry broken.
the image is reversed. Yes. So um, the if one of the incoming particles is a graviton, and now let's consider sending in a particle with less and less energy. That's called a soft particle. And then you consider the limit where the energy of that particle goes to zero. So this Weinberg's soft graviton theorem was a pretty non-trivial formula which relates the scattering amplitude in the limit where the graviton becomes very soft to the scattering amplitude without a graviton at all. And because the energy is so low of the graviton, it doesn't matter what happens in the middle. It's true for every theory you could write down, only assuming it's consistent. It's kind of magic.
And what led Steven Weinberg to be thinking about a question like that in the 60s?
Well, I asked him that question, and he always had a kind of side interest in gravity, but beyond that, this soft um, this soft graviton theorem was discovered at roughly the same time in a completely different language by general relativists in the UK, Bondi, Metzner, and Sachs. And they wrote down a formula which is identical to Weinberg's, but in unrecognizably different notation. And I showed only 10 years ago, 50 years later, that these were the same formula. And I asked Steve, how is it that you and these relativists came up with the same formula at the same time? And didn't know it. Weren't even talking to each other. It didn't even know you'd done the same thing. And his answer was, at that time, everybody was thinking about symmetry, and you just wanted to use symmetry to answer every question every way you could push it. And so that's why he was doing that.
And is that related to you mentioned BMS. Is that related to the BMS symmetries of, asymptotically flat space?
It is the BMS symmetry. In other words, you can derive BMS symmetry from the soft graviton theorem, and you can derive the soft graviton theorem from BMS.
Okay.
But that took 50 years to understand.
Right.
And by the way, these long timescales, like 50 years, are the timescales in this kind of basic research. So if you have a friend who's a basic scientist, especially a theoretical physicist, and you see them, and then you see them again a week later, don't ask them, what's new this week? And if you're these things take a long time to understand, and once you understand it, it's like once you understand it, it sometimes all seems ridiculously simple, and you often can't understand why it is you didn't understand it before. But that's just the way it goes.
Sure.
Anyway, so Weinberg proved this theorem about the limit. And then about 10 years ago, Freddie Cacciazzo and I proved a theorem about the first correction to the limit. And this first correction to the limit, so I just told you that the soft graviton theorem was really Weinberg's soft graviton theorem was a symmetry in disguise. He didn't understand that and by the way, he loved it when this was all put together. And he didn't understand that it was a symmetry, but it is just a symmetry in different notation. And so when we found this subleading, a subleading correction, another universal theorem that had the property that you could say, I don't care whether it's string theory or loop gravity or whatever, I don't care what the quantum theory of gravity is, it must have this symmetry. And so this subleading thing that Cacciazzo and I found had this property. So now if we're going to find the dual to quantum gravity in flat space, it better also have this symmetry. And we know one and only one thing that has this symmetry. And what it is again, the two-dimensional conformal symmetry. And it acts, where is there a two-dimensional surface? Well, the two-dimensional surface is what's called the celestial sphere. It's what you see out at infinity when you look up in the sky. It's the sphere of the heavens. It's out at infinity.
And so one can think about that as sort of the end point of a light ray that's traveling
of light rays traveling from a point in any direction.
Yeah.
That's the celestial sphere. We didn't make up that word. That is what's called the celestial sphere. And there's a really rich irony here, which is if you go back, to the ancient Greeks and so on. So the idea is that the holographic plate must have this symmetry, and therefore the hypothesis of what has come to be called celestial holography is that the dual holographic plate from which our four-dimensional flat space-time emerges is a conformal field theory that lives on this celestial sphere. Okay, this might be, certainly the theorem is a theorem of that these symmetries are symmetries. Whether or not we can really understand the holographic principle this way and make it more concrete, this is work in progress.
Right.
Be claiming something we haven't understood. I can objectively say a lot of people are excited about it, but a lot of people including me, I've been really excited about many things which turned out to be wrong. So might or might not fly. But there's a really rich irony in this because, the ancient Greeks thought that the rules of the universe were written in the heavens. Astrology, that to understand that's where it all came from. The celestial sphere, that's why, for thousands of years, people were tracking the stars with incredible precision. Somehow, to really understand the universe, you had to understand the celestial sphere. And then there was a huge paradigm shift in which starting in the last couple hundred years. Okay, so there's some stars out there, but the really interesting questions are the small ones. Molecules, and molecules are made of atoms, and
Yeah.
atoms are made of electrons and protons, and then those are made of quarks, and maybe so there's been this kind of march in they were going to shorter and shorter distances, and now now we're back out to after a long route, we're back out to where the ancient Greeks were 1,000 years. I think we understand some things that
Yeah.
that they didn't, but you know science doesn't always go. If you try to follow the truth, it doesn't always
Yeah.
lead to where you think it's going to.
So you gave, adequate caveats about the possibility of it not
Yeah,
being right, and, which I,
yeah.
hugely appreciate. But just for the moment, assuming that this or some closely related idea is correct, the idea would be that you could describe all the comings and goings, all the to and froings in the world around us would have a description on the celestial sphere using this conformal field theory description. There'd be an absolutely identical in terms of its predictions, description, but the language would be radically different from the language that we've typically formulated the comings and goings within Newton or Einstein or quantum field theory and so
A
forth.
wild repackaging of all the things we see around us in a different in a different mathematical format, which contains the same information. I'd like to add one thing to connect to what we were saying a little earlier. There is a connection with experiment here. And another thing that we showed is that Weinberg's soft graviton theorem is related to something called the gravitational memory effect. And LIGO hopes that they'll be able to measure that within 5 years of running of advanced LIGO. So we're going to see that. And certainly LISA, these gravity wave experiments in orbit, they're going to see that. And it's going to okay, I don't know. You don't know to see it, but it will be shocking if you don't see that. But this new way we have of understanding things in this subleading soft graviton theorem also makes a prediction for LIGO and for LISA. And there's interest in measuring that. It's called spin memory. And there was just a review published in the last year about what the prospects are for measuring this effect. And, okay, it's maybe an order of magnitude harder than the leading term, but seems could be seen at LIGO. Seems like the kind of thing that might be seen, in our lifetimes.
Yeah.
And LISA will be a very good place
Yeah.
to see it. So we aren't assuming, we're it's a, it's so there's a direct connection with between these observational programs and cutting edge theoretical ideas about the quantum nature of
Yeah.
space-time.
And again, just for people who may not have heard of gravitational memory, the idea being a gravitational wave when it rolls by can leave an imprint on the state of the geometry that it wafted through, as opposed to the geometry returning to exactly what it was beforehand.
Yeah. So another way of saying what you're saying, when a gravitational wave goes by, space gets filled with a lot of these soft gravitons, which have no energy, but that's what the footprint is. So you're still in a vacuum because there's no energy there, but there's a bunch of soft gravitons around.
Right. Beautiful. So I want to two more things if you have patience before we wrap up.
Uh, I'm fine.
Um, you and I don't know if you remember this, but you had dinner at my apartment some years ago. My wife
Oh
Tracy.
boy.
No, no, no. Yeah, and it was. But the reason I bring it up is because in that kind of setting, no one's listening, and it turned out that we had radically different views on quantum mechanics,
Yeah.
and and you forcefully almost castigated me for some of the things that I say about
Well, there
quantum.
was a bottle of wine in between
There
them.
was a few bottles of wine involved. Um, and so I'm just wondering, just to get a sense. So I still am of the mindset that the quantum measurement problem, this idea of, how we go from, the Schrodinger equation description of superpositions and the various weirdnesses that most people in our audience have at least heard about, it all relies upon this probability wave having, non-zero support, non-zero values at different locations, is one way of thinking about it. But when you make a measurement, we all agree that you get one definite outcome. So somehow there's a transition from the fuzzy haze of probabilities to the definite outcome of everyday experience. And it feels to me, and certainly many others, that there's a real issue of trying to bridge the gap between those two descriptions because Schrodinger's equation doesn't allow that to happen. You seem to be less bothered by, at least my understanding from that many bottles of wine dinner was that you were less bothered than I was by that gap, if you will, in our understanding. Is that a correct assessment?
Yeah, and I'll tell you why. Um, somebody was asking me about this was a few years ago now, um, about building a quantum computer, and they were, the head of a big company, and they wanted to build a quantum computer, and they asked me if it mattered whether they used the many worlds or the Copenhagen interpretation. Which should they be using, many worlds or Copenhagen interpretation of quantum? I said, I promise you, if you have two teams and one of them uses many worlds and the other uses Copenhagen, um, they're both going to come up with the same results. Of course, there might be better people on one team, but you don't need to know. So, and the people who, you know, outside the hall there, we've got the formula, 16 digits of, the anomalous moment of the electron.
Probably not 16. A lot, though, but 16?
Yeah, if you include the,
Not that it matters.
yeah, it depends on whether you're taking the minus two. Yeah, okay.
Okay, but
Yeah. The correction. Anyway, so um, um, there's been fantastic agreement between theory and experiment. And I know some of the theorists who did the calculation, and they never discussed whether they were using the many worlds or Copenhagen interpretation of quantum mechanics.
right.
So to me, um, it's not a question that if somebody came to me and said, look, there's an experiment we can do, or even a Gedanken experiment we can do, and we need to say how we understand the collapse of the wave function. So then, then I would be very interested. But to me, it's about the words that you say when you do the calculation. And we can use whatever words you want. At the end of the day, you come up with a number, and that's it. And you know, people often make the statement, and I think in one of your books you quote Feynman on this as saying that nobody understands quantum mechanics, but I don't agree with that. okay, I guess I'm also disagreeing with Feynman. Um, if you can calculate to 14 decimal, that's to me, that's the definition of understanding something. And I wouldn't know how to say what was right unless one gave the right answer and the wrong answer. Now, that isn't to say that I think the questions are uninteresting. There are lots of questions. I mean, philosophy is incredibly interesting, and I have friends who are philosophers, and I enjoy the discussions, and they're like really interesting. But there's some questions that you know, and we never are sure which one there are, right? I mean, it could be that for some funny reason in some context it does matter. It's especially, I think, it might be much more relevant when we want to talk about cosmology, um, the whole universe. When you can't have an external observer. Um, I'm not going to be shocked if somebody tells me we need to have an interpretation of quantum mechanics to make some prediction. But so far, that hasn't happened, and so it's not that I don't like philosophy, but it's interesting, but I am attracted to questions that I can have some hope of answering, and that I can produce an answer that everybody will agree on.
But I guess along those lines, two quick things. There are proposed solutions to the measurement problem, which in principle do have an experimental footprint. Like, for instance, GRW theory, if you're familiar with this idea of putting spontaneous collapse theories, changing the equations of quantum mechanics, actually have an actual collapse of the wave function, but describing that mathematically, not just with words, which, at least in principle, do yield testable consequences. They're hard to test, but at least they're testable. But the other thing that comes to mind is, and this is sort of the more important point, what's the goal of science? So you described it as, once you can make predictions that match experiment to however many decimal points, you've kind of done it.
I don't think there is a goal. I think there's scientists, but I don't think there's a goal of science, because every scientist does and should have their own set of goals.
Good.
Some scientists want to cure diseases.
Mm.
They don't want to understand, how the gene is, the phenotypes of the gene are expressed. Some scientists, want to, build supercomputers or make nanoswitches, and others want to understand the interpretation of quantum mechanics, and they're all good. And moreover, it's I think it's really important that we don't have some
Yeah.
scientists. This should be their goal.
Good.
We're explorers, and every explorer should be exploring in a different direction. We don't want everybody going in the
Yeah. No, I
same direction.
totally agree with that, and I appreciate that. So maybe I'll make it more specific. To the particular explorer that I'm looking at right now, Andrew Strominger, I
Yeah.
would have thought that you wouldn't be satisfied with what amounts to an algorithm for getting a prediction from quantum mechanics. And you want to tell the story, the full narrative of what's going on. And without a solution to the measurement problem, you call it an interpretation, which to my mind kind of denigrates the problem a little bit. Oh, it's just an interpretation. But isn't it really part of the narrative that we would want to be able to tell so we have a complete story of what's going on?
Well, of course, I think that um, the narratives I like to tell are the ones that are spun out of um, some hard calculation that nobody will dispute. And I want to know some things for sure. And of course, of course, I spend lots of time, I spend lots of time thinking about all kinds of things that I won't be able to prove. And is it what does many worlds really mean, or what is that how, what and sort of in wonderment about it. But I don't I don't think I'm ever going to have anything hard to say,
Mm.
and as you know, we spent many hours discussing it. So I I I enjoy talking about it. We're talking about it now. I um, I think it's interesting, and also, what I've been doing recently. Everybody has a different way of their approaching science. There's some people. What I've been doing recently with trying to take the holographic principle and apply it to flat space and not assume string theory, it's a very different game than many of my colleagues have been engaged in, and that is to start from some mathematically completely precise context of string theory and see what you can get out of that. I'm exploring what happens if you give that up and start with some lesser set of things. And I'm not hoping I'm not hoping to find, string theory in principle could be a theory of everything. I'm not trying to find that. I'm not trying to find the theory of, I mean, I work on that sometimes, but I'm not trying to find the theory of quantum gravity that describes our world. I'm trying to understand what we know about our world tells us about possibilities for quantum gravity and how far can we get,
Yeah. Yeah.
Seems like we're getting farther than we have any right to,
Yeah.
So, but getting back to these are interesting questions. They're not my questions, and you about how the interpretation of quantum mechanics, and the reason for that is I like to have the me that's not being interviewed by you when the screen goes off. I'm going to be struggling with my equations in my paper and trying to get some uh, results out of that from which I can say something uh, really definite.
Yeah. Yeah. No,
Um,
absolutely. And look, what you're doing is fascinating. I mean, it's unexpected, I think, to many of us that the words quantum mechanics and gravity in the same sentence might yield ideas that are at least within the ballpark of observational, physics, which is a sort of, wonderful linkage that we've all been searching for in one way or another for decades.
yeah.
So, look, it's been a fascinating conversation. If I didn't have to run, I'd keep going for another hour or two. So maybe we'll pick this up at some other point, in public, or maybe we'll get a couple more bottles of wine and continue the
You're on. You're on.
point. All right. So thanks so much for joining us, Andy. It's been a great conversation, and
Okay.
no doubt we'll cross paths sometime soon.
Yeah.
See you soon. Bye.
Okay. Bye, Brian.